Given any positive real sequence, we're asked to prove that there exists some positive constant k so that the following inequality is true. The infinite sum from 1 to infinity of n over a1 plus all the way up to an is less than or equal to this constant times the infinite sum from 1 to infinity of 1 over an. So for example, the left-hand side is the sum from 1 over a1 plus 2 over a1 plus a2 plus 3 over a1 plus a2 plus a3, so on and so forth. And this Cauchy-Schwarz inequality, I'm going to use it as our lemma. First, because the fact that we have n over a1 plus all the way up to an and 1 over an instantly motivates me to use x1. xj is equal to, this is my motivation, xj is equal to the square root of aj. And likewise, yj is equal to j over square root of aj. J is equal to 1, 2, all the way. So generally speaking, we have the left-hand side is equal to the sum. Right. x1 times y1 is equal to what? Square root of a1 times 1 over square root of a1, right? Plus x2, y2, square root of a2 times 2 over square root of a2 plus all the way up to square root of an times n over square root of an, quantity squared. It's less than or equal to the x1 square plus all the way up to xn square. What is x1 square? All right, that's a1 plus a2 plus all the way up to an. Right. What's y1 square? y1 square. 1 squared over a1 plus 2 squared over a2 plus all the way up to n squared over an. Now left-hand side, 1 plus 2 plus all the way up to n quantity squared is less than or equal to, so perhaps let me just rewrite it into, remember we have the formula, right? 1 plus 2 plus all the way up to n, that's half of n times n plus 1. We raise to the power of 2. What do we have? We have 4 n squared times n plus 1 squared, after we distribute the power. And this is less than or equal to, right, a1 plus an times 1 over a1 all the way up to n over an, n squared over an. Right. Then we can simply just divide both sides by a1 plus all the way up to an and divide both sides by n times n plus 1 squared over 4. Right. So in the end, we have on the left, we have just n over a1 plus all the way up to an is less than or equal to 4 on the top, and n times n plus 1 squared on the bottom, right, times this part, right, this part, sigma j from 1 to n j squared over aj. Right, this is after I divide a1 plus all the way up to, and after I divide n times n plus 1 squared over 4. Right, same thing. So then we just take the infinite sum. Right? This is true for every n, so we let n sum from 1 all the way up to infinity should also remain true. Right? N over a1 plus all the way up to an less than or equal to n from 1 to infinity. This sum, remember this sum, j is changing. Right? N is fixed. Therefore, we can just take this into the sum. Right? J from 1 to n. 4 over n times n plus 1 squared times j squared over aj. Right? Now, I want to switch the order of sum. Now, in order to switch the sums, we're going to just have to look at the table of numbers. X sub 1, 1, X sub 2, 1, X sub 2, 2, X sub 3, 1, X sub 3, 2, X sub 3, 3. The subscript here, first number denotes the row, second number denotes the column. So row 3, column 1, row 3, column 2, so on and so forth, all the way up to infinity. Now let's just use any x and j, right? Nth row, jth column. So this sum, this order, right? First this sum, then that sum. So what this means is that first I fix some row, right? Then I work out the sum of this row. For example, this sum, this row, S3, right? The sum of this row. And the sum of the second row, S1, S2, S1, all the way, right, to infinity. So that way, I can just write it as this way. Look, I'm first holding the row fixed, right? Then I let the column change, right? 3 is fixed. Column goes from 1 to 3, right? Column's changing. So j, right? J from 1 to n, right? If n is equal to 3, right? J is from 1 to up to 3, right? X and j, right? First, I do this sum. Then I sum up S1, S2, S3. What does that mean? That means actually the row is changing, right? N, right? N changed from 1, 2, 3, all the way up to infinity. That's what it means. So, second way is we first work out the sum of each column. Right? So the first column, let's say T1, right? Sum of second column, T2, T3, and so on and so forth. So what does that mean? That means we first hold a column fixed. Right? For example, column 2 is fixed. Right? So it's always 2, 2, 2, 2, 2, right? The second digit is always 2. Then we let the row change, right? Change from 2, 3, 4, all the way up to infinity. So that actually means we first, remember, we hold the column, we hold the j fixed. We let n change from, we let n goes from not 1, but goes from, if it's second column, we go from 2. If it's third column, we go from 3, right? So if the column is j, we start from j, right? To infinity. X and j, right? Then we do the sum of T1 plus T2 plus T3. What's changing now? What's changing now is the column is changing, right? So sum of the first column, sum of the second column, sum of the third column. Column is changing, right? First column, second column, third. So column is j, right? J goes from 1 to infinity. Right, this time column is changing, right? J is the column. So in other words, this sum is really equal to j 1 to infinity. Then we sum. But before we do this sum, right? N from j to infinity. Like n is changing, right? N is changing, meaning j is fixed. Since j is fixed, we can just take out the j square over aj. Over aj, right? Out here. Then we do the sum. N from j to infinity. 4 over n times n plus 1 square. Right? Then we let j move. Right? First we let n move, holding j fixed. Then we let j move. That's what it means. So now I've reached the following inequality. Right? Infinite sum less than this infinite sum. Now I'm going to estimate this expression. 4 over n times n plus 1, quantity square, less than or equal to, by replacing n plus 1 with n, so the whole thing is enlarged. I'm going to further loosen the inequality. First of all, let's look at this integral. This integral from n minus 1 up to n. Function is 4 over x cubed. Right? Function is obviously decreasing function. So decreasing, just roughly. So the area under the curve is obviously larger than the area of this rectangle. Right? What's the area of this rectangle? Simply plug in. Simply the width is just 1. Height is just functional value after we plug in x equal to n, plug into here, right? 4 over n cubed times 1. That represents the area of the rectangle. Is no larger than the area under the curve, right? From n minus 1 to n, 4 over x cubed dx. Right? So in other words, we take the infinite sum, right? N goes from j to infinity. Should still remain true. J to infinity, right? It's nothing but the j. This is simply what, right? So integral, first of all, first integral is from j minus 1 up to j. Second integral from j to j plus 1, then from j plus 1 to j plus 2. Right? So overall, it's simply the integral from just j minus 1 all the way up to infinity. Right? And what is that? First of all, is this integral convergent or not? I think so, right? Because x to the power of 3, right? That's on the bottom, right? Already p is bigger than 1, so power is bigger than 1, so we're safe. So antiderivative. Right? Antiderivative is what? X to the power of 3. right? Minus 2 on the bottom for minus 2 times. So minus 2 over x squared, right? Evaluated from j minus 1 to infinity. Right. That is equal to minus 2, 0, minus 2 plus 2 over. We just have 2 over j minus 1 quantity squared, if I'm not mistaken. Yeah. So in the end, this infinite sum is no larger than this quantity, right? So imagine j is fixed, right? True for every j. So therefore, if we just multiply both sides by j squared, right? Because we have j squared here, so multiply by j squared. So j squared equal j. Right now j fixed, right? So j squared, j to infinity. 4 and times 1 is equal to twice j squared over j minus 1 squared. This obviously approaches 2, right? That's easily verifiable, right? Approaches 2 as j approaches infinity. So right now we can just safely conclude that whatever j is, we can always easily verifiable that this expression is always bounded above, right? Because this has a limit, right? We can easily verify that whenever a sequence has a limit, that sequence has to be bounded. It's easily verifiable. Now, that upper bound, I don't know. Let's just be safe. Let's just use k, right? K is larger than or equal to 2, I believe, just to be safe, right? If it were less than 2, then it may not be true. But if it were bigger than or equal to 2, then you can safely claim that this time, right, k may be 3, maybe 4, maybe 5, whatever. So k is a fixed constant, positive, right? Really exists. Right, so that case, if we just take out the k out of the sum, right, we're only left with 1 over aj, right? So 1 over an, right, different index, but same meaning, right? N from 1 to infinity, right? Same thing. Right? So that way it's really true. Right? The question now is that whether k can be 2 or not, right? Can k be 2? Right? I know for sure that it's safe for us to say that k is bigger than 2. Right? But could k be 2 exactly? The reason I say that k cannot be less than 2 is because that won't be safe. Because remember the definition of limit of a sequence, right? Say, so it's easy for us to show that limit is 2, right? Because we dominating term, right? J squared, dominating term, j squared, right? Coefficient 2, right? So that's why 2 over 1 is 2. Say we have limit is 2, right? So what it really means is that as j gets large enough, every member of the sequence is concentrated enough, close enough to number 2, right? So if we just take so here's 1, take a very, very small open interval. Let's just say use this small interval, right? So as j is large enough, every member of the sequence has to be located inside this open interval, right? So in other words, as j is big enough, after that certain j, every aj has to be bigger than 1, right? Close enough to 2, bigger than 1. So according to this logic, for example, k, if k was 1, then we would be wrong, right? Because not every member, right? Not every member could be less than 1. Right? In fact, the majority of the member, infinitely majority of the member, will be larger than 1 in this case. So we're not safe to use k less than 2, right? But k, larger than or equal to 2, that's okay, right? Because outside of this open interval, there are at most finitely many members, right? Because we already have infinitely many members after a certain j, all living in this open interval. Therefore, outside of this interval, there are at most finitely many, right? Since finitely many members outside of this interval, then we must find a maximum value, right? Perhaps here, maximum. Right? So maybe we can use this constant as our k, right? K is larger than 2, right? That's why. Now, let's say, could k be exactly 2? Right? If we let an equal to n, right, then we say the left-hand side, right? Left-hand side, n from 1 to infinity, right? N over 1 plus 2 plus all the way up to n, right? This is equal to what? N from 1 to infinity. Just half of n plus 1. 2 over n plus 1, right, according to the formula. Then what's the right hand side, right? Infinite sum. Infinite sum. N from 1 to infinity, just 1 over an, right? 1 over n, what is it? Right, harmonic series. So if we just take their ratio, right, divide this over, right, let's find out value of k, right, divide this, right. So in other words, can we find out first let's use the finite sum, right, let's use finite sum. Maybe let's just use n from 1 to capital N, right, 2 over n plus 1 over finite sum, n from 1 to capital N, 1 over n. Then we'll let capital N approaches infinity. Right, in this case, the bottom finite sum as a sequence, a harmonic sum as a sequence, obviously approaches infinity. That's a well-known fact. So we have a sequence on the bottom that's approaching infinity. So we can use Stort's theorem. Right. We can just easily work out the difference between for example, the bottom sequence is Bn, right? We'll work out Bn minus 1, right? Difference between two consecutive terms. So what's Bn? Bn is 1 plus all the way up to 1 over n, right? What's the previous term, right? 1 plus all the way up to 1 over n minus 1, right? If we take their difference, we have 1 over, because the majority of the previous, many terms would already be cancelled out. We're only left with the last term, 1 over capital N, right? Likewise, on the top, right, we also take the difference between two consecutive terms. We have 2 over capital N plus 1. Right? Essentially, that is equal to 2n over n plus 1. Right? Likewise, easily approaches 2. Right? Just, leading term, right? 2n and, right, 2 over 1, just 2. So, which means according to Stolz, right, our original expression also has a limit, right? Also tends to 2. Right? So in this case, the limit, right, meaning the infinite sum, right, ratio really is equal to 2, right? So in other words, in this case, I can say that the infinite sum is equal to 2 times infinite sum. Right? In this case, k is equal to 2. In this case, it's okay. Okay. In terms of switching the order of sums, it may not always be true, especially if we have infinitely negative numbers, like first number 1 and second row we have negative 1, 1. Right? Then we have 0, negative 1, 1. Right? 0, 0, negative 1, 1. Right? 0, 0, 0, negative 1, 1. So on and so forth. Right? In this case, if we add up the first row, sum of the first row, sum of the second row, right? 0. Sum of the third row, 0. Right? Likewise, all zeros. Right? We have this pattern, right? Negative 1, 1 always cancel out. Have zeros. Right? So therefore, when you sum up the sums, we have exactly 1. Right? That's according to the first method. The second method, I'm going to work out the sum of the first column first, right? So T1, right? 1, negative 1, they just cancel out. And we have a bunch of zeros. 0, right? What's the sum of the second column, right? Still 0, right? Bunch of zeros. So in the end, they add up to 0. But in this case, we have different results from different methods. But in this case, we're fine because we have positive numbers. Right? But here, because we have infinitely negatives, that's why. So, may not always be true.